So you have seen how we could make a very interesting device using these semiconductors just by making a p-n junction. From one side it allows current, from other side it does not allow current, and when it allows current, then you change that applied voltage little bit, and you see how the current varies. It varies in a non-linear fashion, exponential fashion. So we have obtained something which is very different from our normal resistances. Okay. So if you have this p-n junction and you have the depletion layer, say this is p side, this is n side, and this is the depletion layer. This is of width x1, this is of width x2, and you connect p side to a higher voltage, that is the forward biasing, and this allows current. What happens? By putting this voltage, by applying this voltage, you lower that barrier, and then the diffusion takes place in large amounts. So if you have electrons here, you have large number of electrons here, majority carriers, they diffuse. So these majority carriers go through this depletion layer and appear here at the edge. Now this is called, so there is a movement of electrons from this side to that side, and therefore a current from left to right. Now this is also known as minority carrier injection. Why minority carrier? These are the majority carriers which are diffusing, and we call this phenomena as minority carrier injection. This injection is in this portion, This is p side, and in p side holes are the majority carriers and electrons are the minority carriers. And we have put in extra minority carriers here, extra electrons here. So that is known as minority carrier injection. And similarly, you have lot number of holes here, majority carriers, and because of this lowering of this barrier, these holes diffuse and appear here on this side. And on this side it becomes minority carrier because this is n side, and holes will be labeled as minority carriers. So this is minority carrier injection. And then for these minority carriers you have a concentration gradient. Now I am talking of the mechanism of current once you have a forward bias. So for these electrons, for example, here you have large concentration here because of this diffusion, because of this injection, and as you go away from the depletion region you have very less number of minority carriers here. So you have a concentration gradient once again, and therefore there will be a diffusion of these carriers. These is now minority carriers which are diffusing from right to left, from the edge of the depletion layer to this contact here, And if this width is sizable, then in the process these electrons can combine with the holes because there are so many holes sitting here. So the electron, when combines with the hole, that charge, stability or the charge equilibrium or steady state condition, that will be disturbed. Okay, because the electron has come from outside and it has gone, that is all right, but the hole has also gone together with it, and if a hole has gone, that means negative charge has appeared. So somewhere that negative charge is to be withdrawn. So this cell which has to maintain the potential difference, and if charges change here, then that potential difference will change. And so this cell will do the required job to maintain the potential difference, that is the That's the job of cell. All that chemistry inside the cell is for that, to maintain a potential difference. And so if this electron combines with a hole, and if this hole goes out, negative charge appears, so one electron has to be withdrawn. So one electron is withdrawn at this contact, and then the electron goes this way, the current goes this way. So similar is the story on this side also. The holes are having large concentration here at the edge of the depletion layer, and on the other side towards that contact they have to diffuse, and during diffusion they can combine with this electron, and one electron can go. And if one electron goes from there, once again the negative charge goes, and therefore this circuit will supply an electron through this contact here to compensate that. So that is how the current goes. And all these things are in a controlled fashion. You control that biasing voltage, and then you control all varieties of the phenomena here and resulting current also. Okay. So on the forward bias side you had your IV characteristics exponentially going like this, whereas on the reverse side you have almost zero current, almost negligible current. If you change the scale here, microamperes, this is milliamperes, then perhaps you are able to see on this plot. So this is what we discussed. Now symbols for this diode. You had seen the diode yesterday. I showed you the actual diode that you obtain in the market if you go. Okay, this circuit we had shown. So that diode is in circuits, all the time we do not draw these rectangles. The symbol for that is, you draw a triangle, this kind of triangle, isosceles triangle, and put a line at this vertex, and then these are two lines here. So this is the symbol for diode. So whenever in the circuit we have to show a diode, we will be putting this. So if I redraw this circuit, it will look like this. I have a cell, I have a resistance, and then I have a diode, and like this. And in this symbol, this side here, this base side, this is known as, this represents P side, and this vertex here and a line here, this represents N side. So when I draw my circuit in this fashion, what I am telling? I am telling that the P side is connected to the positive of the battery, the N side is connected to the negative of the battery. So this is how the symbols are made. Okay. Then for several applications we can approximate our diode characteristic in different fashion, and one application that I will be dealing today, that is known as rectification. I will just tell what it is. Rectification means you have an AC source, AC potential source, AC voltage, and from that you make a DC potential, DC source, DC voltage. From AC voltage you make a DC voltage. Very, very useful thing, necessary thing, because all the power that we obtain in our households is AC power, right, alternating current power. And all the gadgets that we use, most of them, laptop or camera or phone, mobile phones, they need DC current, they need DC power, they need DC voltages to operate. And that's why you always have a charger together with your equipment. And the charger goes in that socket, and the other end goes into your equipment, and in between there is something which actually converts this AC from the mains to DC and then supplies that DC to your equipment. So that making DC voltage from AC voltage is known as rectification, and using this diode, the basic element of rectification you can obtain. But for that I will take a model, or I will model this diode, this IV characteristics. In the forward biased condition, you see that you have large current, at least after some few tenth of a volt, you have large current. So a slight change in voltage gives large change in I. You can say that the resistance here is very small. Whereas in reverse, you apply so much of voltage and you don't get current, significant current, so the resistance is very high, and I'll approximate this as in forward bias. We will assume that resistance is negligible. Resistance offered by the diode is negligible, whereas in reverse bias, resistance offered is very high. Okay. So if I draw a IV characteristics corresponding to this situation, that will be something like this. Okay, it will just it is 0 here, and then suddenly it goes like this. Okay, so this is I and this is V. So for the reverse bias, there is no current, resistance offered is infinity, it's open circuit, it's like open circuit. Whereas once it is forward biased, the diode doesn't offer any resistance, and the current goes very high. Now why this peculiar drastic approximation? Is it anywhere close to the reality? Yes, it is, because for forward bias, the circuit has some resistance. Your circuit has some resistance. So if this resistance is small as compared to that circuit resistance, this approximation is not bad. And similarly in reverse bias, if this resistance offered by this is very large as compared to the circuit resistance, outside circuit resistance, is not that bad. And whatever is happening, we are shifting this line, this large change towards origin, but this is only 0.1, 0.2, 0.3, like that volts, and therefore if the voltages in the circuit in the actual application is much more than that, then that shifting is also not very bad. So depending on what application you are doing, that models are to be developed to understand that mechanism, that physics. Okay. So let me talk more about this rectification, how this rectification is done or can be done, or at least the basic unit can be developed using this diode. So suppose you have an AC source. AC source means your potential V, potential difference V, the voltage is applied, it's some constant times cos or sine omega t, like this. And AC sources are shown by this symbol. So you have two ends, and the voltage which appears here, the potential difference which appears here, is this V. And then let us say you have put this resistance here. Let us say this is just a resistance. What will happen? You know what will happen? You will have a current, and that current will be some V by R, V naught by R cos omega t, that is it. And if I ask what is the voltage appearing on this resistor, so that will be same as the voltage appearing here. If the connecting wire do not have resistances, then whatever voltage is here, potential is here, that same potential is here. Whatever potential is here, the same potential is here. So if I say that this is 0, if I call this as 0, then this potential here will be just V naught cos omega t, and that means it will change sign. So the current will go in one direction and then current will go in other direction and so on. The current will change sign with the frequency guided by this omega. This is angular frequency. So whatever is that frequency, our mains comes at 50 hertz. So if I put my mains here, then this will be 50 hertz cycling. That is what happens when I put my filament bulb or a heater in that socket, 5 ampere socket. So through that heater coil, the current keeps changing the direction, and voltage across that will be again changing the directions. Now what happens if I put a diode in between? Okay, so let me put a diode in between. Let me put just a PN junction here, just a PN junction here, and let me call this point as A and this point as B. So, and this is 0, this is all 0. So what is VA? Potential at A, VA. That will be just the potential difference between the source. So let this be V naught cos omega t, and the question is, what is VB? So if there is a current I, in this direction, then this VB will be equal to I times R, right? Ohm's law between this point and this point. If the current is I, this VB minus 0 will be just I into R. So what is I? And for that we have to use the property of this diode. So if I show this voltage on this graph, time this side and VA this side. So it's just V naught cos omega t, so it is like this. So I should go to the same height and all those things, which I will not be able to do. Like this. Okay, it's not a good drawing, but you bear with me. But let me improve. Try to improve. This should go to the same height. So let it be up to here. Then again it is up to here, and so on. All right. Now with the same scale, if I draw VB as a function of time till here, till this time, what is happening? VA is positive. So this has a positive voltage. This is a positive voltage. Your P side is connected to a positive voltage, and then this will be connected to this 0 side. So higher potential here and lower potential here. This is forward biased. And if this is forward biased, and in our model or in our approximation, we take that forward biased resistance to be negligible, then it is just the old circuit. It's just a short circuit. So it's just this portion is shorted. So you just have a wire and like this. And so your VB will be same as VA, and you will have this part. The same story. I should copy paste here, but I cannot do that. So just like that. After that, during this period, what happens? During this period, this time, VA is negative. So this is at 0, but this is at negative. So that means this is the higher potential side and this is the lower potential side. So P is connected to the lower potential side, N is connected to the higher potential side, and this is reverse bias. And if it is reversed bias and if it offers very large resistance, if I call that resistance as infinity, no current flows through this. No current flows through this. So in that case, this I is 0, and therefore the potential here is same as potential here. V is equal to potential difference is I times R, I is 0. So the potential here is 0, potential here is 0, potential here is 0. So VB will be 0. So this in this period, this VB remains 0. And once again, this potential becomes positive. So in this period, you have a current like this or voltage like this, and the current will be here. Then in this period, you have a reverse bias and the voltage is 0. There is no current. So remove this arrow. But in this period, once again, it is forward bias and you have current. So put that arrow back. Okay. So if I do not put the diode, the current goes in this direction and also in this direction. So it oscillates, the direction of current changes with the frequency given by that omega. But once you put the diode, this current going from this point to this point, this side, this direction is not there. Current only goes in one direction. So current only goes in one direction, and the other part is just 0. So the potential difference which appears across this is in fact a DC voltage. It does not change direction. It's a direct current source. This has become a direct current source. Okay, so you can obtain this DC voltage source from AC voltage source just by putting one PN junction in the circuit. So let me do some experiment here to give you some kind of a feel of this phenomena, and then we'll proceed further. So now I have a unit here which is giving me AC voltage, of which I can control the voltage by rotating this knob, the peak voltage, and from here I can also control the frequency of that AC voltage. The voltage essentially appears here on this cable. There are two wires. In fact, there is one central wire and then you have wrapped coaxial threads, copper threads. So the voltage appears here, and finally I am taking that voltage and taking it at these 2 points. So for me, this is the AC source, of which the peak voltage I can control from here, and the frequency I can control from here. So what I will do is I will take a very low frequency signal from here, and I will put this directly into the galvanometer, so that AC voltage will go into the galvanometer and the needle should deflect on both sides, showing that it is changing direction, the current is changing direction. So first let me do that much of it. So let me put it on, and then I connect this galvanometer, the two ends of the galvanometer, to these 2 points where I am getting my AC voltage. This is connected and this is connected. So you can see that the needle going on both sides, this side, that side, this side, that side. Frequency I can further decrease or increase. So I am decreasing the frequency. This is the minimum I can do. If I increase the frequency, it will go more quickly. Okay, so it is in AC. It shows that it is in AC. It is changing directions. Now, in between, let me put this diode. In this circuit, let me put the diode. So, I put this diode here. Since it is AC, it does not matter which side is P, which side is N. And then you will see can you see it is going only on the right direction. It comes back and again goes towards right. It is not hitting that left end anymore. So, through this diode, once I have put this diode, it only allows current in one direction and not in the other direction. The AC has become DC. If I invert this, what happens? If I invert this, then you see it hits on the left side, not on the right side, because what was reverse bias earlier has become forward bias, what was forward bias has become reverse bias. Therefore, the direction of current is changed, but changed once for all. It is not that every cycle it is changing. This is how your PN junction works as a basic unit of rectifier. If I give a very small voltage, what happens? Let us see. Suppose at this voltage, you do not see any current. But if I remove this diode and I put it here, you can see some current. So, that shows that this assumption that we had taken, that just forward bias and you have large current, that is not true. You have to supply some initial voltage, after which that characteristic, IV characteristic, the exponential part starts, only then it works. So, let me increase this voltage and you can see that yes, now it has started going. All right. So, we will stop today's lecture here. This is a very bad kind of DC. Your DC should be a smooth DC, constant in function of time, voltage as a constant as a function of time. So, next lecture we will see if we can improve this quality of DC by doing something.